So we'll finish the peeling properties today, and then we'll begin with the we'll like begin more physics from it. So right now what we're doing is gravitational waves, and part B, which is consequences of field equations. In particular peeling. And what we saw last time was that we use the definition of asymptotic flatness, plus we use the asymptotic field equations. And what that implies is that the wild tensor should satisfy this condition, x scribe. Right? And then the statement was that this by itself does not imply that wild tensor is 0. I spent some time in explaining that if we had a positive or negative cosmological constant, then it would imply that. But with 0 cosmological constant, CAB, CD, and D equal to 0, this does imply in the Newman-Penrose tetrad that psi 4 at I0, or I call psi 4 bar actually, bar, I0 is equal to 0, same thing, psi 3, same thing, psi 2, same thing, psi 1, but psi 0 need not be 0. And we wrote down that. So these are these two components which don't have to be 0 just from local considerations. But then we've showed that these two components of psi 0 are really contained, these two components psi 0, these two components. Psi 0 is a complex scalar, and therefore it has two real components, and these two components are contained in what this tensor I call CAB to be equal to epsilon A mn epsilon bpq times cnn pq. And this tensor is transverse to n. So if you like, it only has this all at square, just look at. So this is transverse to n, so it only has m bar components, and it is trace free. Times the degenerate metric on scribe is equal to 0. So it's transverse and trace free, and therefore transverse trace free can tensor fields. So this is a tensor field only on a 2 sphere, and it is trace free. Symmetric tensors on 2 sphere have 3 components, trace free is 1 component left, therefore CAB has only 2 components, and these are the components in psi 0. And then I just very in broad brush strokes told you why it is that this CAB has to be 0 if the topology of is S2 cross R. So this S2 was critical there. If this is R, then the statement is that this implies that these properties of CAB and Bianchi identities imply that CAB in fact equal to 0 at scribe. That means, of course, psi 0 is also equal to 0 at scribe. So if topology is 2 cross R, then it is the case that size is that as so then entire wild tensor is equal to 0 on scribe, and therefore we saw that we can define a new tensor which is omega to the minus 1 times wild tensor, and this is smooth. Okay, then this is smooth as well. So that's what we saw last time, and this is called the asymptotic wild tensor. And I emphasize that this is the difference between Maxwell theory, asymptotic wild curvature, and there is a difference between Maxwell theory. Maxwell theory, the Maxwell field itself is not 0 at scribe, and we deal with it whereas for spin 2 or for gravity, and as I mentioned to you, this is also true in linearized gravity, that the linearized wild tensor is also 0 at scratch, and what is not 0 is omega to the minus 1 times that linearized wild tensor. And we extract physics from that. Okay? So therefore we extract physics from that K, B, C, D. And then the statement is that we can again construct scalars from this K, B, C, D, which is M bar B and C M bar D. And now this I'll just call as psi 4. Not psi 4 0, but just psi, I mean not underlined, but just psi 4. That is why I was putting an underline here. I was putting an underline here just to say that A from C, A, B, C, D. The ones which don't have underline, they are coming from A, B, C, D. So these are the physically interesting components of the Y tensor. And then we also, we can do all the Newman-Penrose scalars to be equal to K, B, C, D times last one will be equal to LA, MB, C, and D. And that is defined to be equal to psi 0. So these are just definitions of psi 0, psi 4, psi 3, psi 2, psi 1, psi 0. So I'm not writing all the components. You have seen that several times. Okay. And now what we want to understand is the peering properties up here. So we want to understand that. So we want to understand that if you have, for example, two black holes or neutron stars orbiting, changing their quadrupole moment and emitting gravitational waves, then out at infinity, the structure of the curvature will be different than if they were not emitting gravitational waves. And where is that structure encoded? And the idea, as I told you, was that it is going to be encoded in the psi 4. We are coming to that. So now what we want to do is the following. We want to say that now, look at this K, B, C, D. Let's look at psi 4. We can look at any of the components, but I think if I do it for one, you see what the argument is going to be like. So psi 4 is going to be equal to omega to the minus 1 times C, B, C, D. So that's the same as K, B, C, D times an A, M bar B, and C, M bar D. Right? Now, this is psi 4, but for a trivial reason, I'm going to write it as raise and lower this index. I have not done anything. Okay? I just raise and lower indices, so I have not done any operation. The reason why we do is because the wild tensor has a property that wild tensor with this index structure is conformally invariant. In other words, if I got the metric GAB, our metric GAB was equal to omega squared times G hat AB. This is the physical wild tensor, physical metric. It has a wild tensor, which is C hat AB CD, and the statement is that you just calculate what the wild tensor is, and you will find that this quantity is conformally invariant. So the conformally rescale the wild tensor of the conformally rescale metric is the same as the wild tensor of the physical metric up here. So this is true, and therefore psi 4 is just equal to omega to the minus 1 times, I can just free of charge write this as A, C, B, C, D. But remember, we had various properties of the tetrads, right? How the tetrads are scaled in the physical space-time and the conformally rescale space-time. And then we found that what we want to do is to n hat A should be equal to NA, then hat A should be equal to omega squared times LA, and then n hat A is equal to omega times NT. Okay. So this is the conformal rescaling. So basically, and M bar the same thing obviously. So N L M M bar is a null tetrad for the conformally rescale metric, and the hatted ones, which are rescale, is a null tetrad for the physical metric up here. So what I am trying to do is the following. Just like in the Maxwell case, we know that some tensor field constructed in the conformally rescale space-time is well behaved. Namely, KABCD smooth. And these are all well-behaved tetrad vectors. Therefore, we know that psi 4 is smooth up here. And we're just expressing this psi 4 in terms of the physical space-time quantities. So therefore, I just write down now psi 4. So here it is, psi 4. So n is the same as n hat. M bar b is going to be m bar b is going to be equal to omega to the minus 1 times n hat. But okay, let's go. N is the same as n hat. And m bar d, however, m bar d has a downstairs index. So this is a up here. So to lower the index, I'm going to get a factor of omega squared up here, and therefore this is the same as omega times m bar hat. So basically, the upstairs and the downstairs control factors are different just because the metric itself, as we know, the metric is equal to omega squared times g hat AB. And for the hatted quantities, I'm raising and lowering it. This is g. For the unhatted quantities, I'm raising and lowering with respect to g bar, and therefore that's what we get. And this omega cancels, and therefore I'm left with psi 4 to be equal to that, and therefore psi 4 equal to omega to the minus 1 times psi 4 hat, if you like. This is the psi 4 component of the physical Y tensor, psi 4 hat, in the physical Newman-Penrose tetrad. So this is the Newman-Penrose null tetrad of physical space-time. And the Y tensor of the physical space-time. So Y tensor of physical space-time components in the null tetrad of physical space-time gives me psi 4, except that there is omega to the minus 1 here. And as you know, omega is 1 upon r, and therefore this is equal to r up here. This omega minus 1 behaves like r. So therefore what we are saying is that the psi 4 is really perfectly well behaved at scri, but r or omega minus 1 blow up at scri because omega becomes 0 at scri. Therefore, this is possible only if this decays. What this implies, so psi 4 is smooth. So therefore, this implies that psi 4 hat must vanish at scri as 1 upon r. So therefore, psi 4 hat is going to equal to some quantity which depends on u theta phi upon r. Plus terms of the order of 1 upon r squared. So we use two facts. We use a fact that C hat ABCD with this index structure is the same as C ABCD with this index structure. Okay. It is similar to what we had done in the Maxwell case. In the Maxwell case, F hat AB with 2 downstairs indices was the same as FAB with the 2 downstairs indices. And then the rest is just coming from the rescaling of the Newman-Penrose tetrads in a physical space-time and the conformity rescale space-time. And then what we find is that because we have shown using field equations that KABCD is actually smooth, therefore we conclude that psi 4 naught is going to go like 1 upon r times 1 upon r squared. So this is, so to say, the value of this is the leading value. So this is the value of psi 4. So psi 4 naught of u theta phi is just the value of psi 4. It's just equal to the value of psi 4 of the physically rescaled space-time of physically rescaled tetra components of the rescaled Y tensor K and square brackets. So this is just the leading order per part, which is smooth, and then I get 1 upon r squared. And then you can similarly show that just write down the definition of the various Newman-Penrose scalars, and you find immediately that psi 1, so psi 3 behaves like psi 3 naught of u theta phi upon r squared plus of 1 upon r cube psi 2 naught behaves like psi 2 naught u theta phi upon cube times all over 1 upon r to the 4, and then psi 1 naught similarly. This is boring, but I'll write it once. Psi 1 naught u theta phi upon r to the 4 times plus all over 1 upon r to the 1, and finally psi naught psi 0 is behaves like psi 0 naught u theta phi, and these naught quantities are just the values of psi 3, psi 2, psi 1, psi 0 of the rescale space time evaluated at scri. I just want to make a historical comment up here. The way we are doing it is the following. We just assume that we are given a physical space-time which is asymptotically flat in the sense that it admits conformal completion. And then we use the asymptotic field equations. By asymptotic field equations, I mean we use that limit of omega to the minus 2 times k t hat AB smooth. Or omega to the minus 2 times t hat AB is smooth as Christ. You can take this limit and everything is fine for this density. That is what we mean by asymptotic field equations. That's all. Then the statement is, if the matter fields fall off sufficiently fast, then we know that the Weyl tensor vanishes because of the S2 cross-off topology. And then the statement is, that means that psi 4, psi 3, psi 2, psi 1, psi 0 are all smooth. And the fact that these are smooth in the in the conformally rescale space-time just says that the corresponding components with respect to the physical null Newman-Penrose tetrad would fall off in this particular way. And this is the peeling property. Now the kind of historical remark or the chronological remark is the following, that the way this was first done by Newman and Penrose was really, they did not necessarily assume, by Newman I should say, they did not assume that scri exists. They were using expansions of the physical metric in 1 upon r using a framework that was given by Bondi. And then they said, they just worked the physical space-time. And then the assumption was that if psi 0 falls like 1 upon r to the 5th, then the Bianchi identities and the field equations imply that psi 1 falls off like 1 upon r. The physical psi 1 falls like 1 upon r to the 4th, psi 2 as 1 upon r cubed, psi 3 as 1 upon r squared, and psi 4 as 1 upon r. That's what they showed. So they started in the physical space-time, but assumed that psi 0 actually falls like this. And then everything has followed. So they also assumed asymptotic expansions, which actually do imply that you got the conformal completion is scri. Here we did the other way around. Here we just assumed that the conformal completion exists and the fields are smooth, and then arrived at the properties here. To me, this is slightly better in the sense that we are not assuming this. Right? This is not necessary so long as we actually have the conformal completion that is given to you. This is important because sometimes in literature you might find a little bit, the results which are stated in a way they may seem to be in conflict, but if they are not, in the physical, if you start with the conformally rescale space-time, then you do not have to assume how psi 0 falls off. We just assume that psi 4 or k, b, c, d is actually smooth, and that is something that comes from the fact that the metric, the conformally rescale metric is smooth. Yeah. See.
So you have a hat on side 4 and none of the other ones? I just wanted to know if
side 4, where here?
at the bottom, yeah.
Oh no, those were all hats. I'm so sorry. These are all physical. Thank you. So physical, the components of the physical Weyl tensor in the physical null tetrad fall up like that. That is the statement. Okay. And now this is suggesting, this feeling is suggests, and it is not a proof of anything, we're going to see that this is all true, But what this suggests is that psi 4 naught should be thought as radiation field. And as I was telling last time, in the numerical simulations of black hole collisions or gravitational waves in general, what people plot is this psi 4 naught. Okay, so that is a typical field that you will see that is being plotted. We're not done. I mean, I'm just giving you the first cut, if you like, as to why psi 4 naught might be radiation, because it falls like 1/r, everything else falls faster. So the statement is that this psi 4 is supposed to be, so yeah, so psi 4 is radiation field. And then the second thing is that as you go down the ladder, you get psi 2, and then psi 2 naught has the Coulombic information. Now, why is this the case? Because recall that if you have static spacetime, for example, Schwarzschild spacetime, then the physical metric G hat AB is equal to eta AB, the flat metric, plus terms of the order of 1/r, which go out to infinity. There are no time derivatives up here, which go out to, and then in that's okay for Schwarzschild. And if for static spacetimes, you can check that as a result, when I compute the curvature tensor, or the Riemann tensor, or the Weyl tensor actually is a second derivative of the metric, so therefore it is actually following that as 1/r squared. 1/r squared. And in fact, for Schwarzschild, the Weyl tensor is exactly that. So in Schwarzschild, the Weyl, if I take the Gravitational scalar, as I told you last time, that is following like 1/r to the 6th. Right? So the only component in Schwarzschild spacetime, the only component of the Weyl tensor which is non-zero, the physical spacetime, is just psi 2. Everything else is 0, and psi 2 is falling like this. And the coefficient here is the mass, right? So the statement is this 1/r2 times some coefficient, and I think it is 48 pi. I think. I'm not sure. No, just 48 maybe, times gm squared. So this is the reason why 1/r³ part of the Weyl tensor carries information about mass, carries the information of the Coulombic aspect of the field. Coulombic aspect of the field is like what gives rise to this force in Maxwell theory, the force between two charges, and similarly it gives rise to force between the test particle. It governs the orbit of the geodesics, and that is really this quantity, or if you like, tidal force is all given by this CABCD, and that is captured in psi 2. So these are the two things. Psi 4 has radiation information, and psi 2 has information about the Coulombic aspects of the mass, the total mass of the space-time, total energy of the space-time. Okay. Are there any questions about this? Yeah.
So coming back to like the way that you're doing the derivation versus the original way, in your derivation you kind of assumed that like we have this conformally rescaled metric, and like we want like our fields to behave well and like nice physically there.
Yeah. So C3, everything is C3 set.
And from that, like this data follows. Then I could be very annoying and just say like, well, the conformally rescaled metric doesn't actually exist, so why do we need physical restrictions on that?
Right. So exactly. So the statement is that information is encoded in the fall off of the in the fall off of the physical spacetime metric. So to motivate it, you would have to say that physical spacetime metric behaves in a certain way. So if you like, historically, that's what really did happen. Namely, Bondi and others wrote down a framework in which they said that the physical metric, you look at those metrics which in some chart behave like this. And then you can show that those metrics have made this conformal completion up here. So you're completely right. That there's no a priori I would not know that this is the correct definition. So this is more like packaging. The final result is this, and this is the best way to present it. That is really the best way to look at it up here. the advantage of this for me is really that you can see what the structure is in a transparent way. If you say that there exists a coordinate system in which the metric has this fall off, then for example, you can still analyze the asymptotic symmetry group and so on and so forth by using those properties. But it is really quite tricky to do it properly. I mean, in fact, that's how they did it in the first time. Bondi, Meissner, and Sachs, that's how they did it. But it's quite tricky. And we'll see now here in the conformal picture, it is easy, and hopefully we'll finish it today. Okay, so that is really the. Okay. There's one other thing, that in the Maxwell case, we saw that not only was, in that case, phi 2 fell like 1 upon r, which was the radiation field, but also it was freely specifiable on Scri. Right? You did not have to, there were no constraint equations on it. On the other hand, the lower components in Maxwell theory, which are phi 1 and phi 0, they, at Scri, their time derivative was governed by what the radiation field phi 2 did. The same thing is true here. Psi 4 can be specified freely, whereas the time derivative of psi 3 is determined by psi 4. Time determined here is determined by psi 2, etc., etc. But those equations now are nonlinear and they're much more complicated. And therefore, I'm not writing them down. Hopefully, I'll write them down before we finish, but therefore, I'm not writing them. So therefore, the same motivation there holds here. Okay, so now what we want to do is the next step. And the next step is the following. We have extracted now what we mean by radiation field. So then the next topic is really extracting physics. So we would like to say, okay, if they are gravitational waves, they are probably encoded in psi 4. We've not completely finished it. We're going to come back to this and justify it in much more detail. But we still would like to extract physics. See, in Maxwell case, we have two things. We have the Poincare group, right? This is just a French joke way of writing Poincare. Point is a point, and carre is a square, so it's Poincare. Okay, so this is a Poincare group, and then the statement is that in Maxwell case, and then the generators of this Poincare group are time translations, space translation, rotations, and boosts. That is a 10-dimensional group in 4 dimensions, and we got this. And the statement is that we use this time translation to define energy. Energy is the generator of time translations. Momentum is the generator of space translations. And angular momentum is a generator of rotations, and relativistic angular momentum is a generator of rotation and boosts together. So that's what we do in ordinary field theory. So we use these symmetries to define causal quantities and quantities from which we can do physics. For example, in the case with if you have two black holes and they collide, and supposing the collision, they give rise to they emit gravitational waves, and supposing these gravitational waves are carrying a lot of free momentum in this direction, then by conservation you would expect that the black hole would move in the other direction, just like a jet fluid, right? It's like a modern jet. The fuel is really the gravitational radiation, gravitational waves, and therefore the black hole might be ejected from the galaxy. And these things are taken very seriously by astrophysicists. But then to really arrive at these conclusions, I need to know what I mean by three momentum. Similarly, people would like to say, well, if I got neutron stars, then these neutron stars, there may be some accretion, etc., or they might actually be losing angular momentum through gravitational waves very, very slowly, but still. And therefore, their evolution will be such that they will rotate slowly as time goes on. But to calculate this, I need a notion of how much angular momentum is carried away by gravitational waves. And the same thing about energy also. But in general relativity, we don't have a symmetry group, right? So here we got the Poincare group. The reason why I got the Poincare group is because we have a fixed metric. So not just Maxwell theory, but any theory in special relativity. So Maxwell or more generally in special relativity. So it can be Klein-Gordon field, it can be Dirac field, it can be the scalar field. For any of these fields in your quantum field theory books that you've seen, the statement is that for all of them, there is a fixed metric which is common to all these fields. You may have one Maxwell field or the other Maxwell field, you may have Dirac field, you may not have Dirac field. It doesn't matter. The metric is still there. So this is, so to say, a universal, this metric provides us a universal structure, right, background structure. I say background because it doesn't depend on which field I'm talking, how big that field is, etc. That's why it's universal. This is common to all of these fields. So this is common to all these fields. And then symmetries, Poincare group, as you know, is the group that preserves this metric. So we get the flat metric eta AB, flat metric which is eta AB up here, and that is the Poincare group preserves this. Now in the infinitesimal form, the Poincare generators let us call them fancy PA. These are the vector fields in physical space-time which generate, which are killing vector fields within Gaussian space, so, and they satisfy PA of eta BC equal to 0. So lead derivative, so they lead rank eta. Finite diffeomorphisms, metric is preserved, means that under infinitesimal diffeomorphisms, which correspond to vector fields, infinitesimal diffeomorphism is always a vector field, and then the metric is preserved under this. So we did two things. First we said, well, there is a universal structure. What is it? And we found that the universal structure is this metric, and then we looked for the diffeomorphisms, subgroup of the diffeomorphism group, which preserves this universal structure. And that gives us a symmetry group. And this is true in every branch of physics. It could be, in this case, it is supposed to be the standard Minkowskian physics. In string theory, you may want to deal with only background being an anti-de Sitter space-time, and then the metric eta AB is really the anti-de Sitter metric, and therefore the symmetry group is going to be the anti-de Sitter group. So this is universal. This is also true in Newtonian mechanics. It's also true, in every field where it's also true in quantum mechanics. All the symmetries come from some universal structure, and the symmetries preserve that universal structure. So this is really very, very, very core of physics, and doesn't matter if it's classical physics, quantum physics, relativistic physics, non-relativistic physics, general relativity, etc. So what we would like to do is to find out if in fact to talk about the energy, momentum, etc. Can we do it? Well, we can do it if in fact there is a symmetry group that I can use for systems, for space-times which represent gravitational waves, or systems which are radiating. So the question that we want to ask is now that for full general relativity, we don't have, the only group we have, or we don't have any preferred subgroup. Of the diffeomorphism group. M is a space-time manifold and diffeomorphism group. We don't have preferred one. And therefore we don't have any of these notions. We cannot do this rich physics if you just consider a full realm of general relativity. It is diffeomorphism covariant theory, and I just can't do anything. I cannot define energy, momentum, etc. However, for the sector of general relativity, which consists of asymptotically Minkowski spacetimes, so these are only representing isolated systems. So I'm excluding cosmology that you were asking me about. I'm just looking at isolated systems. Metric falls off at infinity, so that you have got a conformal completion that is allowed. So for the sector of general relativity, which consists of asymptotically Minkowski spacetime, it is indeed true that there is so we can do all those things. So for this, there is a universal structure, non-trivial universal structure, which is common to all space-time. So I may have space-time representing Schwarzschild. I may have a space-time which is a Schwarzschild space-time representing a static black hole or a static star, or a Kerr space-time representing a rotating black hole, or two black holes which are going around emitting gravitational waves, etc. It's quite nice. It's quite impressive that all these diverse situations have a nice universal structure at Scri. That as you go out to infinity, the structure of the metric simplifies and we get some universal structure. And therefore this universal structure is preserved by some group, by a subgroup of the diffeomorphism group. And this subgroup of the diffeomorphism group is the symmetric group, or people call it asymptotic symmetric group. And this was analyzed first by Bondi, Mesner, in the axisymmetric case, and generalized in a very beautiful work by Sachs to all cases, not necessarily axisymmetric case. So it is a Bondi, Mesner, Sachs group, and it is called the BMS group. So you might have heard about BMS group many times, especially in string theory literature, etc. It is now becoming very fashionable to find BMS group everywhere, and even in cosmological spacetimes and such things. And what we want to now do is to understand what this BMS group is. So our task is twofold. First, find what is a universal structure for asymptotically flat spacetime, and then find the group which preserves it. And that is what we're going to do now. So our third part of the talk should not have anything there. It's just the next few parts. Extracting physics is our next part up here in general, and the third part of it. So the 2.c is going to be the universal structure. Of asymptotically Gaussian spacetimes. And then we'll see what is a subgroup of the diffeomorphism group which preserves this universal structure. So now what is a universal structure? So this is a structure common by that we want fields. In this case, we got geometrical structure, so various fields. So for special relativity, it is the metric eta AB. For in string theory, for the asymptotic, for physics on anti-de Sitter spacetime, it will be anti-de Sitter metric, and so on. So the structure of there is a fields common to all spacetimes under consideration. So the space, as I said, the spacetime have radiation, spacetime may be stationary, spacetime doesn't matter. So long as it is asymptotically flat, I always have this structure. So what is this structure? So this is what we want to say. So the first part of the structure is that it has the admit a boundary. Whose topology is Scri, which is topology E_2 cross R. And again, I'm using Scri to really mean Scri plus or Scri minus. So I'll just call about Scri here. What is of interest to us is Scri plus, where the radiation emitted finally lands up. So let's suppose it admits a boundary which is Scri. Then on this boundary, it is null. So if I look at Scri intrinsically as a 3-manifold, what structure does it have? The definition I wrote down a couple of times when we studied gravitational waves, and also when we did black holes. That implies that we have a vector field NA. It is ruled by this NA vector field. And I got a metric QAB of signature 0 plus plus. This is just the pullback of the conformally rescale metric to Scri, this metric QAB. And Scri is a null surface, so NA times QAB equal to 0. So that is the only degenerate direction of QAB on Scri. That is precisely this vector field NA we got. So NA now is the null normal. We can think of it as null normal, and QAB is the degenerate metric. And also we went to the divergence-free conformal frame, which told us that in the physical space-time, that in the space-time picture, in the conformally rescale space-time, we got graph A and B equal to 0 at Scri. So what this implies immediately, if I pull, so this is of course the same as, this implies that Lien, this implies two things. This implies that Lien, so in particular the symmetrized derivative is 0, so that implies Lien of the full metric GAB, conformally rescale metric is equal to 0. What I'm trying to do here is look at structures which are intrinsic to Scri. So this is why it is in parenthesis. I'm just recording for you what we have seen up here. And this, of course, immediately implies, if I pull back this equation, if I pull back this equation to Scri, then I just obtain Lien of QAB equals 0. So, we got a vector field NA and a degenerate metric QAB. The only degenerate direction of QAB is N, and what we know is that Lien of QAB is equal to 0. So this is what we have as Scri. It is a manifold which is S2 cross R. It is a vector field and it satisfies that, which immediately tells us that we can think of Scri as a cylinder. So this is S2, this is R. Remember in our coordinates that I used last time when we systematically introduced coordinates up here, I can take here theta phi, and up and down Scri I can have coordinate U, which is an affine parameter of N. So NA, graph A, U equal to 1. So I got a affine parameter up here, up and down. And so, what I know is that this manifold Scri, S2 cross R manifold Scri that I got up here, it is ruled by this null geodesics, right? By these null rays, NA. So I got these null rays up here. These are the integral curves of NA. And Lien of QAB is equal to 0. Since the signature of QAB equal to is 0 plus plus, that means just like what we saw from the horizons, where I got a intrinsic metric QAB, but given a cross section, I also have a two-sphere metric. So this is a two-sphere metric on this cross section. Let's call it C. And on this cross section, on the cross section C, QAB, I can pull back QAB. QAB exists everywhere here. On 3 manifold, I can put it back to the cross section, and that is equal to SAB. In other words, the statement is that QAB is degenerate. Because it is degenerate, all the information in QAB is contained in this SAB. There is no information in the vertical direction up here. And furthermore, it is actually lead dragged by this vector field up here. Well, when things are lead dragged like that, it is convenient to go to the manifold of orbits. In other words, project down Scri to sphere, which I'll just call S. Okay? So this is a two sphere, which I'll just call S up here. So every point up here is, so this point up here will be this. This whole generator will be projected down to this point up here. Right? Star up here. This generator projects to this. This generator, cross generator projects to this. This dot generator projects to this, etc. So this is the space of generators. A generator is just the integral curve of NA. So of this vector field NA that I got, and I project down, I get a two sphere up here. And what we see up here is that this metric QAB, because it is transverse to M and because it is lead drag, it projects down. And I get here a metric, let's call it Q bar, a bar AB. And since I got a projection mapping, pi, which maps each generator to a single point, I can pull back covariant tensor fields. And so the statement is that the pull back, which is, people will call it pi star, of Q bar AB equal to QAB, or in our language, I can just take Q bar AB and pull it back via this pi map, and I will get QAB. So the content of this metric QAB is really on this two sphere metric. Okay. So the whole thing is rather simple, right? I mean, I'm saying that you've got a cylinder, right? I mean, this is one dimensional load. This is just S1 cross R. Instead of that, we've got S2 cross R. We've got a cylinder. The cylinder is ruled by integral curves of NA, and I'm given a degenerate metric which is orthogonal to this and is lead drag. So nothing happens for the metric in this direction. Non-triviality of the metric is just in the S2 direction, and therefore I can project it down and I obtain a metric on the two sphere, and I got this QAB. Now again, the fact that the two sphere is going to play an important role, because it turns out that the conformal group of a two sphere is isomorphic with the Lorentz group in 4 dimensions. We're going to come to that in a minute, but I just wanted to, I like to say this thing a few times so that you sort of start thinking about it and then you understand it well when we actually do it. So this fact is going to play an important role. The fact that this two sphere is an important role. If this was not a two sphere, the symmetry group will not be the bonding as a size group, it will be completely different, will not have peeling, will have, everything will be very different. Okay. So, at the moment, the only thing you have to remember is that what we have is really this universal structure. S2 cross R, a vector field in R direction, a metric, if you like, in the theta phi direction, so that they are actually orthogonal to each other and is lead drag. And therefore, we've got this ruling of Scri by integral curves of NA. Every integral curve is called the generator of Scri. This is just a terminology. And the space of generators is a two sphere. And if you like, the metric that we have got up here is really lives here. It just pulled back from here, it just dragged up here because it doesn't change as you go from one point to another, and it has no component in the n direction. So it really is all in this direction. Good. So now this is the universal structure. It was quick. And now the symmetry group. So it's simple to state. You see, in terms of coordinates, I find it always a little bit hard to state. I don't mean that logically there is anything different in doing it in terms of bonding Mesner's a bonding chart and then looking at diffeomorphisms which preserve the follow-up of the metric in a Bondi type chart. In other words, the diffeomorphisms, how many Bondi type coordinate systems are allowed, that is what will give you the BMS group. But here I find it much more streamlined and can be done much more quickly doing this. Okay. So therefore our third part is already over. So fourth part is the BMS group. This is a symmetric group. Asymptotic symmetry group of asymptotic linear Gaussian spacetimes. So that's what we're now going to do. But we already saw what the symmetric group is supposed to do. Finite symmetric group is the diffeomorphisms on scri. So the DMS group G, or let's call it B. DMS group, let's call it B. This B is a subgroup of the diffeomorphism group of scri, which preserve the universal structure. And therefore, the Lie algebra of this, the infinitesimal ones, this consists of this is the space of vector fields. Such that I have to write down what I mean by preserve the universal structure. But I'm sorry, I realized just a minute ago that I actually did not finish specifying the universal structure. There was one subtlety that I left out. That is why I left this room up here. But I forgot to mention to you that subtlety up here. And that subtlety is the following. So sorry, I'm going back for just a minute to the universal structure up here. That you know that in the physical space-time, the physical metric is G hat AB. Right, the physical metric. And therefore, GAB, the conformally rescaled metric, was given by omega squared times G hat AB. So I got this rescaling freedom, omega squared. I got this rescaling freedom up here. And so, therefore, I got a freedom in choosing omega goes to omega prime to be equal to, say, little omega times omega. And what conditions should little omega satisfy? Well, for our boundary conditions to be whole, I think we've seen this several times before, but let me repeat. It means that omega cannot be 0 anywhere on scri, and ln of omega should be equal to 0 on scri. This condition comes just because we want to preserve this condition, if you like, ln of GAB equal to 0, or this condition, grad A and B, because we are in diversity conformal frame. Because of that, the restricted gauge freedom, the restricted conformal freedom I have, is that where little omega satisfies this condition on scri. So under this, what happens? Well, QAB obviously is just a pullback of GAB. So under this, the statement is that G prime AB then is going to be equal to little omega squared times GAB, right? Because I'm just multiplying by little omega for this conformal factor. So if I G prime AB would be little omega squared times G hat AB, and therefore it is just omega squared times this. And what about N prime? N prime A will be G prime AB times grad A, grad B of omega prime. And I should really write this as grad prime, but since it's a gradient, it doesn't matter which derivative operator I choose. And therefore, this object is just given by omega to the minus 2. Since G downstairs is omega squared, therefore this is omega to the minus 2 times GAB, grad B of omega omega. And therefore on scri, I apply this grad on this product. When omega comes out, that term will be 0 because big omega is 0 on scri. Therefore, only little omega comes out, and I get here on scri is equal to omega minus 1 times GAB, grad B times NA, plus some big omega comes out, and then I get omega to the minus 1 times GAB, grad B of little omega. But this term is 0 on scri because big omega is 0 on scri. So what we see up here is that where I got this universal structure, and this, however, there is also conformal freedom. Namely, I can have QAB, Q prime AB, and N prime A. These are also allowed if, in fact, the relation is that this is equal to QAB and omega to the minus 1 times Na. So I don't have preferred Q and N on Scra. I got a pairs of Qn, but the pairs are restricted. If you give me one Q, then to get another Q allowed, I have to rescale the old one by omega squared. And you are giving me N, then to get another allowed N, I have to rescale it by omega to the minus 1 up here. So that is the structure that we got up here. So this is now coming back to the diffeomorphisms. So what do the diffeomorphisms have to do? They have to preserve the universal structure. That means if you give me a metric QAB and a vector field NA with one completion, I can make a diffeomorphism. The diffeomorphism doesn't have to preserve the metric. It can map the metric to omega squared times the metric. But if it maps the metric to omega squared times the metric, then it should map NA to omega to the minus 1 times NA. So let me write down that first. So the BAB, this thing is supposed is a diffeomorphism, is a subgroup of the diffeomorphism group of Scri, such that if the diffeomorphism group D maps QAB, so first of all it must map it to conformably rescale QAB, and then so this is the image under diffeomorphism NA should be equal to omega to the minus 1 times N. Okay, so this is the diffeomorphism acting on QAB. You must give me this again, where linear of omega should be equal to 0. This is what we see. Linear of omega is identically 0 on star. So those diffeomorphisms which map the pair, the metric and the normal and the vector field NA, they should map them proportional to themselves. But the proportionality factor is not arbitrary. If the metric is mapped to omega squared times QAB, that omega should satisfy this condition. And if the metric is being mapped like that, then NA should be mapped by omega to the minus 1 times NA. So the BMS group is a subgroup of the diffeomorphism group on Scri. So I can have these diffeomorphisms on Scri which do whatever you want, but it should map NA to omega to the minus 1 NA, and the metric to conformably rescale metric. So in particular, it means the following: that this diffeomorphism can take the generator and send it to that generator. So the diffeomorphism can be like that, for example. But if this point on this generator is mapped to this generator, since the diffeomorphism must map NA to something proportional to NA, this ruling is preserved. So this in particular implies that the ruling of Scri is preserved. NA is not preserved, but the integral curves of NA are preserved. So the ruling of Scri is preserved up here, and the metric is rescaled. Just by confound factor, or metric just rescaled. So you might imagine the metric is just mapped to some other metric. No. The metric, the generator should be preserved, and the metric should be mapped to something proportional to the old metric with this proportionality factor, which is tied to the proportionality factor by which n was rescaled. Okay. So this is the BMS group. That's it. That's the BMS. Now what we want to understand is what is it? I mean, what is the structure? And what we are going to see next time is that its structure is very similar to the Poincare group. In the Poincare group, it has 4 translations and 6 Lorentz transformations. Right? That's what we got. And the translations form a normal subgroup, as we'll see next time up here, and they're abelian. Same thing is true here. The BMS group has an abelian normal subgroup, and if I take the quotient of the BMS group, the abelian normal subgroup, I get some other group, the quotient group, and that quotient group is again the Lorentz group. So in the language of group theory, the BMS group is also a semi-direct product of an abelian group with the Lorentz group. Just like the Poincare group is a semi-direct product of translations, which is the abelian group, with the Lorentz group. The difference is, and this is the striking difference of the big revelation when it first came, that the abelian subgroup is infinite dimensional, and it's called the group of super translations. It's not 4-dimensional, it is infinite dimensional. That is sort of a big revelation. And the reason why this big revelation came, I just want to say one more thing and then I'll stop, is because, why this was a revelation, is because everybody had assumed that we're talking about asymptotically flat space-times. So if you're given talking about asymptotically flat space-time, that means that at infinity, the metric is just flat, it's just Minkowski metric. So of course, asymptotic symmetric group would be the Poincare group. And in perturbatory quantum gravity, this is a standard assumption that the symmetric group is going to be the Poincare group. And what this says is no, symmetric group is not a Poincare group. It's a huge enlargement. So in the beginning, there was a lot of confusion about where does it happen? And we're going to understand it both mathematically and physically. What happens is that if there is gravitational waves, then these gravitational waves send out ripples, even at infinity, that shake the Minkowski metric, if you like. In other words, if the physical metric approaches the Minkowski metric, and if there is gravitational radiation, then this physical metric can also approach another Minkowski metric as 1 upon r, satisfying all our conditions or satisfying the boundary conditions, where the new Minkowski metric is not the same as the old Minkowski metric, but differs from the first Minkowski metric by angle-dependent translations. We'll see this in much more detail. Again, I'm just saying it several times so that you get the gist of it. And this is a big surprise, that in presence of gravitational waves, the asymptotic symmetry group is not the Poincare group. It is a much bigger group, and this has very important ramifications. From the perspective of quantum field theory, or from the perspective of quantum gravity, this happens because of infrared behavior of the gravitational field. In other words, this happens because the gravitational field falls only as 1 upon r, not faster. If the gravitational field were falling faster than 1 upon r, this would not happen. This really has to do with the infrared behavior of the gravitational field. So this is what we're going to see next time.